So we're going to be talking about Cats Effect 3, which I am very, very excited about. We've got a little sort of contest going on with Josh Surratt, who is sort of unfortunately in the same time slot as me. So if for some reason you're watching this talk as opposed to his, you should use this hashtag on Twitter and spread the good news that he is actually a full stack YAML engineer and not whatever he claims to be these days. In the category of things that are more interesting, stay tuned to the end of the talk because we've got a special announcement coming up. So that'll be exciting. But before we go into the details of the talk, I want to take a moment to actually just thank a couple of people here. So there's the Cats Effect 3 has been a monumental effort, and there's been a lot of people involved, but I really do want to say an extra special thanks to this collection of professional headshots, the Charizard and the Top 10 Anime Betrayal, for just being like a fantastic group of people who have done so much work to make this possible. So I definitely don't want anybody to get the impression that this has been the me show. I think these people have done considerably more work than I have to make Cats Effect 3 a reality. But with all of that said, let's just kind of dive into what's going on. So what we're going to do is we're going to talk about what is coming in Cats Effect 3 and what it looks like, right? And the very first thing, the very first pillar of design that we went with here is a focus on convenience, completeness, safety, and user experience. We really want Cats Effect 3 to be an extremely pleasant library to use, extremely convenient, to have what you need out of the box, a little bit more batteries included. And this is a slightly different focus than what we've had in the past, and I'll talk about that in a little bit. We did a complete rework of the core calculus. So this is kind of like what Scala 3 did, where they kind of took a step back, thought about the math, came up with the dot calculus, and then Scala 3 came out of that. We did basically the same thing for Cats Effect 3, and the naming is just a coincidence. And the results are really, really great. I'm very happy with what we've been able to come up with, and I think it will show in terms of users using it in real world situations. With a shiny new IO implementations, like completely new encoding, new ideas behind it, and it's really, really, really cool, both from the standpoint of something that you can look at if you want to see how a production IO works, because the implementation actually is very concise and easy to read, despite the fact that it is so highly optimized, and it has a lot of really nice properties and sort of natively supports these features. And the performance results are really, really good. I don't usually like to talk about performance when it comes to effect systems because there's usually more important things to talk about, just frankly, but it is worth dwelling on this a little bit. Cats Effect 3 is a meaningful step up, not only above Cats Effect 2, but of the ecosystem as a whole. It really is, it really raises the bar in that regard. So let's focus on user experience first. This is my favorite screenshot ever. Because it shows me being completely incompetent. This is a GitHub issue that was opened ages ago against Cats Effect, asking for a function that creates an IO from a completable future. This is a very natural thing to want, right? And especially if you're working with something like the AWS SDK, which I don't know, approximately 1 billion people do, this is something that you really need. And we didn't do it. It's not in Cats Effect 2. I closed the issue and right away, it was like, well, what's going on, right? And I think that's a totally reasonable thing. And the reason this was closed goes back to a lot of different factors, right? So Cats Effect 1 was created about 3 years ago now. And it was really born in a completely different time. It was intended to be a minimal foundational framework, very little surface area, very, very, very stable. We had this sort of hubris that we would make one release of Cats Effect 1 and then never release it again. That was kind of the idea. And it was meant to foster an ecosystem, right? It was meant to address this need in the Scala ecosystem at the time that just wasn't really being met by what was there. And it was designed for that. And we've moved on. But it led to this design philosophy where we just wanted a basic set of very simple primitives with just really absolutely nothing else, and then leave the rest to the ecosystem. So in the case of completable future, Monix Catnip has a completable future conversion. So we were just like, why bother putting in the core? But honestly, we've learned a lot since then. Okay. And I don't just mean Cats Effect 2. I mean, the whole ecosystem has kind of learned a lot. The Scala is in a different place than it was before. Functional programming is very much in a different place than it was 3 years ago. So it's time to take some of those lessons into account. So a little bit of a reality check, right? People use IO directly. Um, this was something that I actually wasn't anticipating when we first designed Cat's Effect, and that shows, right? Like it really shows that that was sort of a surprise. Um, Most people honestly use IDEs. This is one of the ways in which Scala has changed, especially over the last 5 years. IDEs, the rise of metals, like things like that, it's just completely, almost universal at this point. There's just a few weirdos like me who still use text editors. Um, Dependencies are scary, and they have not gotten any less scary. This is just a fundamental thing that comes from the linearity of the JVM's class path and the fact that it's just a string. So I think dependencies on the JVM are going to be scary until we address that issue. And this means that having a very wide ecosystem, a very sprawly ecosystem, can be a little nerve-wracking for people because if you don't trust Monix Catnip to continue releasing things on schedule, then maybe you don't want to add it to your class path. And like, I get that, I really do. So it kind of speaks to this out of the box experience. Like when you sort of put Cat's Effect into your library dependencies, you should have a really good out of the box experience. And like, yes, there is functionality that is in the ecosystem, which is amazing, right? I mean, we're never going to fold an HTTP server into Cat's Effect. We're never going to be a streaming library like, FS2, but there's some basic stuff that should be there and that you would expect to be there. And I think it's time that we really address that. Another major one is the user base has grown a lot, right? The user base of Cat's Effect, when it was created, was kind of bounded by the user base of Cats and the user base of ScalaZ, which, at the time were much more niche than they are today. I mean, it's still a relatively niche ecosystem compared to something like Play or Spark, but functional programming is a lot more mainstream now than people realize, and Cat's Effect has been a major part of that. So it's really important that we treat this quite consciously, like it's a much broader ecosystem than it once was. And literally every member of that ecosystem is confused about the semantics of async and shift, which is an element of Cat's Effect 2 that I take full responsibility for because it's terrible and it was my bad idea and I really insisted on it. And then there's this whole category of like 1,000 Papercuts stuff. So we've already talked about completable future, right? Like trying to address these things in Cat's Effect 3 is really a major goal. And it will continue to be a major goal even after Cat's Effect 3 is released, because I imagine things will shift over time. But from completable future, it's on IO. You can just get it. And to note, by the way, this is a JVM only thing, right? Because Scala.js actually doesn't support from completable future. So on Scala.js, we have a from promise. So if you happen to have some promises floating around, you can just get them into IO very, very easily. We have read line and print line on IO itself. This is a deceptively difficult thing to do, by the way. They're there, they work, they interoperate with the sort of JVM things like set out and set in, in exactly the way that you would expect. All that stuff is good. We have an interruptible combinator. Now, this is something that not a lot of people think about, but if you have something that is blocking, obviously you want to move it off of the main thread pool, which we'll talk about in a little bit. But you also sometimes want to make it something that can be canceled because blocking things, you want to be able to shut them down. The JVM has a native interruption mechanism, but it's really difficult to work with and very difficult to get right, and it's not really compatible with Cat's Effect's interruption semantics. So this interruptible combinator does it for you. So you don't really have to worry about it. So this interruptible, thread sleep thing, that thread's going to sleep for a long time, but it is a cancelable fiber action, and it will handle the thread interruption and make sure everything is cleaned up, and you don't really have to think about it. Execution context. So this is one of the things that Cat's Effect 2 is sort of infamously bad at. The execution context semantics of Cat's Effect 2 are kind of left up to you. You have to thread things around yourself. Cat's Effect 3 takes a much more first-class approach to this, where the execution context is something the IO manages for you. It hands you one. You can change it, like you can specify your own, but you're always going to have one available, and you can always just summon it by asking for IO execution context. And that is so useful, particularly when interoperating with libraries which need executors for whatever reason, right? Now you no longer have to thread that around yourself or ask your users to provide it, which never works. Here's actually like a pretty fun example of something that would be really painful to do in Cat's Effect 2. You can paste this into a REPL. So you can literally copy paste these lines into a REPL. Right at the top, we have an import of the unsafe global runtime, which is what you want to use if you're in the REPL and ideally nowhere else. And then this program just runs exactly as written. If you've ever tried to do something like this with Cats Effect 2, it's kind of a pain. You have to set up your context shift. You have to set up your timer. Like you have to kind of like configure your pool and figure out like what's going on. Here, it's just right out of the box and no extra imports. Like everything just works. So this kind of like early experience, again, it seems like a minor thing to a library author, but for users who are trying to even just get off the ground with a library, this kind of thing is very important, and we treat it very seriously in the design of Cats Effect 3. Another fun thing, so this picture is courtesy of Zelenia, who also drew the Cats Effect logo and a number of other logos here. So Dispatcher, which I'll talk a little bit more about later, is a brand new thing in Cats Effect 3. Really, really innovative construct, I think. But basically, it's this discovery that we can kind of invert the notion of callbacks even within the framework of the async type class. And that allows us to solve the interrupt case where you're trying to deal with frameworks that want to run code unsafely, frameworks like Play, frameworks like Akka. If you wanted, for example, if you wanted to have an actor that actually, handled one of its messages using an implementation run inside of IO, Dispatcher is a way you could do that actually a lot more safely than any ways that were previously available. And this is really, really exciting to me because it solves a major pain point in the ecosystem as a whole in a way that I think is quite novel. So user experience it has been a major focus, and I think will continue to be major focus. So I don't intend to be closing any more bugs of the type of completable future to IO anytime soon. Calculus. So the core calculus of Cats Effect 3 has been redone. Literally rethought from scratch. And this is the thing, we've been thinking about this for like 2.5 years, give or take. Like there's been a serious amount of time on this, and it's gone through a lot of iterations. But the principles we've been following are basically this, right? Simple things have simple foundations. And Cats Effect 3 has a simple foundation, a simple foundation that supports a lot of complexity and power. And this was basically the goal, right? Can we distill down the number of fundamental concepts and axioms, really, that define the Cats Effect 3 runtime system to a really small and clear set that, like, okay, you have to like work pretty hard to understand what each of these is, but once you get it forever, and then everything else comes out of that, right? Like trying to get to that point with something as complicated as an asynchronous runtime system was an immense technical challenge, and I think we've really got it. Barring a couple of things that maybe we could have done better, but like I'm really, really happy with what we have. Each type class, which is really the sort of container for these axioms, is self-contained, it's lawful, it's heavily tested, and it's very, very practical. So every single element of this was really, iron forged against the practicality of the question. We didn't just sort of like go into a mathematics vacuum and come up with stuff and then be like, well, this is the way it's going to work, and we'll just make the practicalities contort to that. Everything was very, very carefully tested, and that did lead to some compromises with the mathematics, right? Things that felt right from first principles that we could build some nice properties around and some proofs around turned out to be bad ideas because in practice they just didn't work out so great. And that is why, working with the ecosystem this whole time has been so valuable. The whole thing is a very small, very orthogonal set of primitives. Each sort of core fundamental primitive function in the type classes, which is to say each core fundamental function in IO, is very self-contained. It doesn't have functionality which overlaps with something else. Everything is very discretized. This means, among other things, like there's really one way to encode things, because anything else you just actually won't have the primitives to do it. And it also means that if you understand that one thing and its implications, then you understand this whole range of functionality which comes out of it. You don't have to remember these special rules in your head. So again, it's like one of those things where I'm okay with concepts taking a long time to really understand, as long as we don't need to do that with too many of them, right? As long as everything else emerges from that. And that's really what we wanted to do. I also want to digress briefly on the lawfulness point. One of the big problems with previous type class hierarchy is a lot of the laws were basically just like, okay, complicated program, equals pure of something, right? It was just basically just, an assertion of equality. And like, that's functionally okay. Like, there's nothing actually wrong with that, but aesthetically it feels wrong. And the guiding principle that we kind of went with the laws in Cats Effect 3 is that every law should be a substitution rule, similar to what you would see in mathematics, where like, parentheses a plus b close paren plus c is equal to a plus parentheses b plus c, close paren. Like you can do that rewrite in either direction and you get the associativity property of addition. All of the laws in Cats Effect 3 are like that. And in theory, most Cats Effect 3 programs could be interpreted in terms of these substitution mechanics, right? Just basically sort of substitute your program like over and over and over and over and over again. And you'll always find a rule to do it. And then eventually you'll just get the semantics of your program out the other side in terms of things that you do understand. The hierarchy is now safe. This is a completely underappreciated point, I think, especially when people start off with Cats Effect 3. But and I'll talk more about this very briefly, but like the goal was to make it so that you could use the hierarchy and get exactly and only the functionality that you want out of it, that your function for that point needs, and not functionality that you don't need. And this, for a library like Cats Effect, which is dealing with arbitrary side effects and things like that, that's a very difficult thing to do. And I think we've really accomplished it. So an example of where this shows up, if you just have a random function like this, right, and so it takes an f context and the f is concurrent, in Cats Effect 2, concurrent means async and it means sync, which means that you can capture any side effect, right? This can launch the missiles, it can launch the missiles asynchronously, like it can do anything. It can fiddle around with futures, and it has concurrency, right? In Cats Effect 3, if I say something is concurrent, I mean it has access to concurrency and nothing else. It does not have access to like do arbitrary things with the file system or something like that. And this little change actually just makes reasoning about programs so much easier. So this is a fairly dense diagram. It's kind of difficult to digest in a little bit. This is on the Cats Effect 3 README if you sort of go and look at the series 3.x branch. But this diagram shows the new hierarchy. It's very different from Cats Effect 2, but you'll notice that the red type classes, async and sync, are now at the bottom of the hierarchy, right? And we're just going to go through each of these super quickly and talk about each one, but they all have a very clearly defined purpose, right? So monad cancel, right? This is the top part of the hierarchy. It's kind of a little bit like bracket used to be. So it has bracket on it, but it also has this sort of uncancelable, on cancel, and canceled, which are really powerful tools. And in particular, uncancelable has been generalized significantly from Cats Effect 2. It's now this much more granular thing that's also very composable, right? It used to be that you would sort of cover things with an uncancelable region and then you couldn't get out of it. Now you can, right? You can poke holes in your uncancelable region in this safe way with this pull thing that you can see on the screen right here. This function with permit, by the way, was impossible to implement in Cats Effect 2. Like you actually couldn't do it. And what's interesting is it's also impossible to implement if you don't, in a composable fashion, if you don't represent your uncancelable in this way. Like if you just have like an uncancelable and then a cancelable or something like that you can just try to nest inside each other, eventually you end up with semantics in this function which don't compose anymore, and like more uncancelability wraps around it and starts to break things. Uncancelable pull is something that Fabio Labella came up with, very inspired by some Haskell functionality, and it really addresses this issue in this extremely elegant way. So I mean the definition of with permit in Cats Effect 3 is just like very obvious once you understand what uncancelable does. So that's a really exciting thing, and that's already had huge impacts on the safety and comprehensibility of the ecosystem with respect to interruption. Spawn. So spawn is the next type class down the line. This is what gives you fibers, so green threads, right? And the diagram here on the right kind of shows you the limitations of just spawn, right? So these little edges represent data flow, so you can sort of spawn off your fibers and then join them back together. But the edges in the middle that have the X's on them, that represents things that you can't actually, like, data can't flow in that direction with just spawn, right? You can't take data from the middle of a fiber and then put it in the middle of the next fiber and then continue on. That kind of referencing is impossible with only the spawn type class. So this is the image I have in my head. But spawn still provides provides you with some nice functionality. Start and seed, which is kind of like the yield functionality for fairness. All the parallelism, par tupled and things like that come from this. It also has race, which actually is terrible for reasons that are academically very interesting, but it's also extremely important. So we have it. And this is just par tupled. You can access that. One thing that's fun about this is that a common gotcha in Cats Effect 2 is that you would have, say, a concurrent instance in scope for a particular F, and you would want the parallel functionality, the par tuple, par map n, something like that, but you couldn't get it because concurrent did not imply parallel in Cats Effect 2. Now that's not the case anymore. So if you have a spawn, you have a parallel, and you just don't need to worry about it, and these functions are just available to you. Again, like focusing on these ergonomics a little bit more closely. So concurrent. Concurrent is the next type class down the line, and this is where we get unconstrained data flow. So those edges that I said you couldn't have, now you can have them. And the way that you get them is with ref and with deferred. These tools are now part of the type class hierarchy. So you can get at them directly out of the type classes, and there's functions on IO, for example, for accessing these directly. So they're very, very much there. The ref and deferred are primitives that are very, very, very powerful, and you in practice need them with almost any concurrent application because they give you these extra edges that I had previously X'd out, where like the data flow can kind of flow between the fibers. And they tend to lead to very, very clean state machines that are, it's easy to do the right thing with them. So putting them in the hierarchy makes a lot of sense from first principles. It makes a lot of sense practically. It solves a lot of problems. And it means that the concurrent type class is generally a good bet. Like that's usually pretty much what you want. Temporal. So this is the next one. Again, moving down the line. This doesn't correspond to timer. Timer was kind of this thing on the side. Temporal is like this brand new thing that just does sleeping and timers and like gives you the sort of JVM monotonic clock and the real time and handles all the details of doing this on JavaScript, etc. Sync. Sync and async, I think we pretty much understand these. Sync, has delay, which we know and love. It also has interruptible and blocking, which is new. Blocking replaces the old blocker abstraction. So now if you have a sync, you have the ability to capture an effect that is blocking, and you can just say it's blocking, and the runtime system will do whatever is necessary to make that work. You don't have to worry about threading a blocker through your application anymore. And then finally, async, which is the sort of final type class in the hierarchy. It can do literally anything. One thing that's interesting that's been added to this is eval-on and execution context. So eval-on existed in Cats Effect 2, but it didn't really behave the way that anybody expected it to. This is all sort of sorted out in Cats Effect 3 and the execution context that I showed you before. So for example, this snippet here in Cats Effect 3, the too cool for pool execution context is going to be used to run FA, regardless of what FA is doing. And FA might have its own eval-ons, which kind of change things recursively, but too cool for pool will be used preferentially by FA, regardless of how much asynchrony it's doing or anything like that. And my favorite part about all of this is that concurrent effect is gone. So any of you who've used libraries that are forced to bring in concurrent effect, things like, HTTP4 as row or STTP or things like that, concurrent effect is kind of a pain. Like it really prevents you from doing a lot of advanced things with the system, particularly sort of context threading and things like that. But as it turns out, async alone is enough to provide that functionality and to provide it in a way which works really well with compositional effects. And that's just extremely exciting. So so that's the new hierarchy. There's lots more to talk about here. We're just kind of like going through this at light speed, but I am very, very excited about the set of primitives that we've come up with and the effect that they have been having on the ecosystem so far and the effect they will have in the years to come. So IO. Now, the IO monad in Cats Effect 3 has been completely greenfield implemented from scratch. We literally just started from a new editor buffer and went from there. So completely from the ground up. It has a strong notion of fiber identity now, which is really, really helpful, particularly for implementing things like fiber locals and tracing. There are 0 allocations during interpretation of the system. So basically, and I should clarify, it's sort of 0, amortized. But when you're interpreting an I/O program, the interpreter will not actually add any allocations to that whatsoever. Everything is just the I/Os themselves, which is about as good as you can do on the JVM or at least in Scala, with the constraints that we have in terms of how we're the abstraction that we want to have with I/O. Arrow in Kotlin is able to do a little better because of the compiler functionality. But in Scala, I think this is, zero interpretation is about the best you can hope for. We also have very, very, very carefully designed memory barrier semantics. So if you're familiar with performance on the JVM, particularly around concurrency, you know that memory barriers are this double-edged sword where they're very, very expensive because they require a flush to main memory, which is very, very slow compared to stuff that's directly on the processor. But they're also very essential, right? You can't necessarily make data visible between threads deterministically without using memory barriers. And the I/O monad, the I/O implementation that we have, very heavily exploits memory barriers and memory fencing semantics to both on Intel and on ARM to make sure that data is published appropriately between threads, but we don't take any more performance penalties than are absolutely necessary. And in practice, this has a huge impact on the performance and responsiveness of the I/O runtime. And we also, this is something I'm really excited about because it's probably the very first thing anybody will notice about Cats Effect 3, but we have a deeply fiber-aware set of schedulers for both JVM and JavaScript. These schedulers, I'm going to talk a little bit more later about some of the performance which comes out of these, but these schedulers are insane. Like, they really make a huge practical difference in major applications. We've seen as much as 2 orders of magnitude performance improvement in cases that are very, very practical and realistic. Usually it's more, a little bit saner than that, but I don't think any enhancement that we've seen has been less than like 2 or 3x. So it's a substantial jump, and I think you'll see that right away in your application when you start using it. So just for fun, I thought I would dive into the actual implementation of I/O because it's easy to kind of gloss over this. Oh, I/O is magic, right? Well, let's actually deconstruct the magic. So here is the I/O encoding in Cats Effect 3. I'm doing things using less efficient types. So we're using like list here to represent a stack, and we're using either and things like that. This is not actually what Cats Effect 3 does. There's more efficient encodings of these data types which don't require allocations. But this is basically the idea. You have a stack of continuations, and each continuation is this function from sort of, either an error or a value to, the next IO. We have a canceled flag, we have a final result, and we have a set of listeners, give or take. And then everything else is machinery around this. So then in the core of the interpretation, in the run loop, it basically looks like this. First, with each iteration of the loop, we take the IO that we're trying to interpret, we check to see if our fiber is canceled. If we are canceled, then we're just going to kind of tell the listeners and then stop. But if we're not canceled, what we do is we just take apart the IO. Is it a pure? Okay, it's a pure. Let's take our continuation stack and sort of send the value to the continuation stack and let the run loop continue with that. If it's a flat map, I included this because it's interesting, right? We have to push something onto the continuation stack, which is the F that you handed to flat map, and then we invoke the run loop on the the value that's inside the flat map, and away we go. And the whole IO is basically done in this fashion. And this sort of gives us 2 stacks, right? One is the call stack of run loop, which we basically make that tail recursive, so it's no big deal. And then the actual continuation stack of cunts, and everything sort of flows through that. So this abstraction is actually really nice. It's really, 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 really fast. And it's actually pretty easy to read. So if you actually go into the implementation of I/O, it looks like this. I actually copy pasted this from I/O, and you can see there's some encoding in here, right? We're doing this tag thing, which is weird, and like there's these integers, and like we do some casting because what's performance sensitive code if you're not doing casts, but you can see it's pretty similar to what I had on the previous slide, right? And the whole I/O interpreter is like this. So one of the nice things about this is, like, honestly, it's not that difficult to contribute changes and fixes to Cats Effect 3's I/O. Like, it's not scary. Just like go in there and make some changes. Test Suite is very comprehensive. It'll catch you if you do anything wrong, and it's pretty easy to sort of manipulate functionality, add stuff, like fiddle around with it, and learn lessons about how to do very, very, very performance sensitive code on the JVM and particularly in Scala. So there's some cool stuff in there. Check it out. So speaking of performance, it's hard to talk about I/O without talking about performance, and I do want to clarify that, like, performance in the context of effect systems is usually a red herring. Like, there are more important things with effect systems, and I have basically never had an application that was ultimately gated by the performance of its effect type, even when we used to use things like Scala Z task, which was like several orders of magnitude slower than anything we have today. It's usually not a thing that's kind of a bottleneck, but it can be more impactful than you might think, particularly at this higher level of like sort of contention and orchestration and like things like that. And you know, the goal with Cats Effect 3 when we started out was, you know, let's get the performance to where it was for Cats Effect 2. You know, that was basically the intention. I mean, Cats Effect 2's performance is good. It's been deployed at scale in production by, you know, many companies. It's, you know, we know that it's good enough. The goal was to get there, and we matched that and we exceeded it by quite a bit. But even more importantly, in the process of doing that, we discovered some things that we were able to get out of performance that would have been completely impossible in Cats Effect 2, and which don't exist in any other asynchronous runtime. At least not on the JVM. There's at least one in Rust, I think 2 in Rust that do this, and there's a couple other languages. But by and large, this is basically the next frontier of effect system performance, and Cats Effect 3 is right there at the front of it. So I actually have some results to show you. Now, I will clarify, and I'm going to have more disclaimers about this later, but I will clarify, every benchmark is lying to you, right? Like nobody's benchmarks are actually accurate because nobody's benchmarks other than your own are run on your application, okay? So be very careful about the lessons you take away from this. I think these are pretty good benchmarks, but like, you know, run your own tests. Always run your own tests. Don't take my word for it. You know, please don't take my word for it. So contention scatter gather. Here's like the idea behind this test is it's a severely high contention workload. Maybe you've got a service that's doing some sort of typical scatter gather, you know, request response pattern. Requests come in, you make like 10 requests in parallel, comes back, and then you're just putting a shit ton of we compared the fixed thread pool with the Cats Effect 3 scheduler implementation. And the results pretty much look like this. Cats Effect 3 is literally 55 times faster than a fixed thread pool. And this is on the same hardware. We did this on a 32 core machine. It actually gets crazier if you give more and more physical threads to it, just because of the way that this stuff works out. But 55 times, like, that's a lot. Okay, even if this isn't like a totally applicable benchmark to your use case, 55x gives a lot of wiggle room for other stuff. Let's look at another scenario, right? I gave you the best benchmark first, but like let's look at the ones that sort of aren't quite as flattering. Okay, so concurrent heap pressure. Most of the code that we write these days in production is sort of, you know, a microservice that sits in the request response path. It takes a request, it parses some JSON, it transforms that JSON, it produces, serializes some JSON, and sends it off to somewhere else. This is like 70%, 80% of Scala code right now. And what's interesting about that workload is it's not particularly heavily parallelized, but it does a lot of heap pressure in the critical path, right? Because you're serializing and deserializing to these JSON ASTs that we tend to use with libraries like Circe and stuff. So what does this look like? Like, again, comparing fixed thread pool to the Cats Effect 3 scheduler, trying to get things as close to apples as possible. Well, this one, Cats Effect 3, also comes out really substantially ahead. I mean, it's not 55 times anymore, but 2x, give or take, you know. And again, this is trying to measure not just like some micro benchmark thing, like how fast is flat map or something like that. This is trying to measure the types of things you will see in your performance metrics on your service running in production. That's what we're trying to measure here. Very hard. I mean, we're not succeeding because we're not your service, but like that's what we're trying to get at. And the results are far more than I thought they would be. You know, when we started down this scheduler path, I thought we'd get like maybe, you know, 10% if we were lucky, and we're actually seeing, you know, 10x. So it's really insane how much we've gotten out of this pool. These benchmarks, by the way, are basically why I'm not interested in Project Loom, because Project Loom makes this impossible. Like, we actually can't get access to the tools we need to get this performance if we allow Loom to handle the scheduling for us. So that is why Cats Effect 3 does not have a special Loom backend, because it would actually be slower by like a lot. So it's just not worthwhile. Final benchmark, I promise. I know a lot of people aren't as interested in this stuff, but I wanted to go a little bit further in the sort of realistic category. We wrote there's a library called FS2 Netty, which is very, very, very new, which just wraps around Netty in a purely functional fashion using Cats Effect 3 and FS2. So it's a very high level library, right? And the idea is, let's implement an echo server in here, and then let's implement an echo server by hand using the Netty framework, which is very difficult to work with, by the way. And let's see what the performance looks like. Let's just sort of hammer on it with TCP Kali and various benchmarks, and see what this actually looks like. And I did this on my laptop, by the way, because I was lazy, but it is using the KQ backend from the BSD kernel. And so let's see here. Apparently the animation screwed up, but okay. So raw Netty versus FS2 Netty with Cats Effect 3, raw Netty wins. Nobody should be surprised by that. What's interesting here is how close it is. This is what surprised me. So this raw Netty thing is like super cheaty, right? Like I hand tuned this. We're like using direct byte buffers and we're not freeing them. We're sort of passing them through to the response path. We're doing stuff, you're using a single handler. We're doing stuff that you actually couldn't do in a general fashion, but because it's an echo server, it's easy. The FS2 Netty thing is like super general and like purely functional and craziness. And look, it's like within, what is this, like 12, 15%, something like that? That is crazy. And this is an aggregate throughput, by the way. So 12, 15% on aggregate throughput. So to be really clear, this is the whole echo server, right? It's this like super generic thing. You can read this code, you can refactor this. You could actually see writing like complicated network protocols on top of this type of framework. And it's that fast. Like it's almost as fast as hand-tuned Netty. That hand-tuned Netty was, if you don't know Netty really well, you're going to have a hard time doing that. Whereas this, the framework is just going to guide you and it's just going to work. And because of Cats Effect 3 and FS2, you know that the performance is going to be really, really good. And in fact, I will make a very bold claim here. I will say that Cats Effect 3 is the fastest asynchronous framework on the JVM. For some definition of fast. We'll get to that really quickly, but like it is the fastest thing that we have benchmarked against. And we benchmarked against everything in Scala. Like there's nothing that really lines up with it. And it's competitive with hand-tuned code, which is, I don't make that claim lightly. So some definition of fast. Again, I will say this again, benchmarks are lies. They only measure what they measure. Cats Effect 3 does really well in common micro benchmarks, like stuff that that we use, stuff that we used on Cats Effect 2, stuff that Monix uses. Those measurements make Cats Effect 3 look really, really good. And these new benchmarks that we've been trying to come up with that measure practical things looks good in those too. Does that tell you like what is going on with your application? No. You have to measure your own application. Look at your own metrics and you tell me whether or not the performance is good, right? So that's basically like, how you should treat these kinds of benchmark results. I think they're exciting, but like, are they exciting for you? You need to find out. So try to be as representative as we can, try to provide as many caveats as we can to make it clear like what we are and are not measuring. So the sort of applications you write in Cats Effect 3, these are really, really good, but try it yourself and find out, seriously. So Cats Effect 3, it would be remiss to talk about Cats Effect without talking about the ecosystem, which again is something that has changed massively over the years. And like I ran out of room on this slide. I also ran out of projects that have real logos, but like the ecosystem is large and sprawling and growing significantly. And there's so much amazing stuff in here. Like the ecosystem authors are incredible people. And we've been working very closely with all of these projects and many more through the Cats Effect 3 process to not only refine the design and make sure that it meets the needs of the ecosystem, but also to find problems with the ideas, right? And to make sure that everything is coordinated so that when we are ready to release Cats Effect 3, the ecosystem is right there with us. And you can have, a great experience right out of the box as an end user. So speaking of releases, we need to get this out the door. Cats Effect 3 has been in development for like, really 2 years now, 2.5 years. The ecosystem has been like along for the ride, like all that stuff. At some point you just have to shove it out the door and get it in users' hands, and you can tell us how good it is. So today, literally right now, I am announcing that we are going to release the final version of Cats Effect 3 on March 14th, 2021. So a month from today, we will release Cats Effect 3. And I think you will all be very, very, very pleased with the results.